Let's look at a problem involving forces on an incline. So here we have a sled. There's a little bit of friction with this mu equals 0.1. We know the incline is 20 degrees, and we want to find the acceleration that the sled has. So we can start this out, right, with a great sketch like we just have, and we can use that sketch to then help us draw an interaction diagram. So we have our sled, and we want our sled to be our system. And we want to know what's in contact with our sled. Well, the hill or the incline itself, and then nothing really else in our sketch. There is a non-contact force with the earth. So the non-contact force is, as you are guessing, the force of gravity, and then between the sled and the hill we have a normal force. And because we're given a coefficient of friction, we also know we have a friction force. So these are great interaction diagrams. That leads us to a free body diagram. So a free body diagram, we're going to kind of draw the hill itself, and we're going to kind of draw the horizontal for it. And we can draw our sled as just a dot. And let's start drawing forces for this. So we have our force of gravity is going to be in straight down. Our normal force is going to be perpendicular to the surface. And then our friction force is going to be right along the surface, but pointing backwards. We'll have a friction force like this. Now, it might be one option to think of having a normal Cartesian coordinate system, x and y, like this. But I'm going to say, let's not do that, right? It's going to be a lot of a pain, and we'll tell you why. So the reason why is that our force of gravity is one force, and it is aligned with this coordinate system, but our other two are not. And also the motion of this sled, the sled isn't going to go in the x, it isn't going to go straight in the y, it's going to go along this surface. So if we choose a right coordinate system, if we choose a coordinate system that looks like this, then our sled is actually moving just in one dimension being easier than two dimensions. What do we call these two? So you could call this y prime and x prime. I'm going to use the perpendicular symbol and the parallel symbol because the y prime and x prime leads to another problem that we can confuse ourselves a little bit later with. So that is what's going on with this. Now we know that our friction force is just in one direction. It's negative F in the parallel direction. Our normal force is just in one direction. It's positive N in the perpendicular direction. That's really cool. Our force of gravity is going to be a little bit more complicated than that. And we can take a look at it. So we can kind of decompose it as much as we want into this perpendicular and parallel. And in fact, that's going to be such an important and such a useful little thing that we're going to really blow it up and draw it over here, just so we have full understanding and full confidence with what we're doing with this. So again, we have our force of gravity going straight down, and then we have our decompositions of that force of gravity with as good of a 90-degree angle as I can do. So this is Fg in the perpendicular direction, this is Fg in the parallel direction. And what we saw right here is we have this angle and this angle. Well, these two are, funnily enough, right, parallel to each other. So whatever angle this is also this angle. So let me draw that here. With the horizontal, this is going to be 20 degrees. We know that our force of gravity is straight down. This is straight horizontal. So this total angle of this one plus this one has to be 90 degrees, which means that this angle has to be 70 degrees. If we look at it that way, then we have 1, 2, 3 angles for our triangle, and all three of them must add to be 180 degrees. So we are saying, right, 90 plus 70 plus question mark equals 180. If you feel confident, right, you can say it, but also try to pause the video, try to solve for this. Okay, welcome back. So as we've solved for it then, 90 plus 70 plus 20 will give us 180 degrees. So why do we use parallel and perpendicular instead of x prime and y prime? It's because of this next part. To find FG perpendicular, it's going to be fg times one of our two trig functions. And the trig function that we use is the one that is for adjacent. And the one for adjacent is cosine. So it's going to be mg cosine theta. And this is interesting because, right, if we said y prime, we might confuse y prime with just having to use sine. If we want to find fg parallel, that's going to be mg times the opposite, so that's going to be sine theta. If you want, right, for our cosine of 20 degrees will give us 0.94, so this is going to be mg times 0.94 for later. And if you want for sine, this is going to be mg times 0.34. This makes sense, right? 20 degrees is a very small angle, so most of the components of fg should be in the perpendicular direction, and a very small amount of it should be in the parallel direction. So we've found this, and now we can do what we need to do with our Newton's second law. So Newton's second law says that our acceleration is going to be the friction plus the normal plus the force of gravity over the mass. And then what we can do is we can decompose into the perpendicular and parallel directions as opposed to x and y. And we'll show you why this is also very nice. So in the perpendicular direction, friction is 0, normal is normal, and as we said, we got fg perpendicular, so we have mg times 0.94. In the parallel direction, we have friction is negative friction, normal is 0, and then we have mg is positive, mg times 0.34. And we divide both these by the mass. So right now, we don't know too much because we have both an acceleration perpendicular and acceleration parallel. We don't know either of these. We don't know the normal force. We're in a little bit of a bind. But if we think about it, can this sled move through the surface, or can it float above the surface? And if we think about it enough, we'd say, no, it can't, right? Also, we have a normal force. Normal force means the acceleration perpendicular to the surface is 0. So, funny enough, we have this perpendicular right here. This is 0. So, looking at this then, we can then say that, right, 0 equals n minus mg cosine theta over m, or that n is mg cosine theta. And this friction we know is equal to mu times n. So if looking down for here, we use a different color. We have that our acceleration parallel is going to be negative mu n plus mg times this sine theta, or 0.34 in this case, over our mass. And now we can plug our n in, and so we have that our acceleration parallel is negative 0.1 times mg cosine theta, 0.94, plus mg times 0.34 over our mass. Well, why did we not specify the mass of the sled? Because we have a mass term here, mass term here, mass term here, so our masses cancel. And now we just have numbers, right? We can plug in g is 9.8. We can rearrange a little bit nicer if we want, so we can say factor out g, and then we have 0.34 minus 0.1 times 0.94. And if we do all of that, then we should be able to get g times a very small number, and we get that our acceleration in the parallel direction is 2.21 meters per second squared.